Welcome back. On the deep dive today, we're digging into something quite neat in mathematics transformations that act like bridges. Specifically, the Cayley transform.
Ah, yes, the Cayley transform, named after Arthur Cayley back in 1846. And what's really key is that bridging idea you mentioned. It's less one single thing and more a cluster of related mappings. Started out connecting skew-symmetric matrices to special orthogonal ones.
Okay, building bridges, cluster of ideas. Sounds powerful. But how does one transform actually, stretch across so many different areas? We're talking real numbers, complex analysis, even Hilbert spaces.
Right, it does seem like a lot. Think of it maybe as a kind of mathematical translator. If we start with the simplest version, the real homography, it works on the real number line. It can, for instance, permute specific points like 1, 0, 1 on the real projective line. It sort of rearranges things.
Rearranges the whole line. Okay. And I read this has practical uses. Something about mapping positive reals to the interval AA1, 1, which helps with adapting things like Legendre polynomials.
Exactly. It lets you take techniques usually meant for finite intervals and apply them to rational functions defined over, an infinite domain. It's a way to make infinity a bit more manageable for certain calculations.
Right, taming infinity. I like that. So what happens when we move to complex numbers?
The complex homography. It gets even more geometric there. The standard form is fzzi divided by z plus I. And what it does is pretty cool. It takes the entire real line and wraps it perfectly onto the unit circle in the complex plane.
Wraps the line onto a circle.
And, maybe more importantly, it maps the entire upper half of the complex plane onto the unit disk.
The unit disk. Okay, now that rings a bell. Isn't that fundamental for hyperbolic geometry, connecting the Poincaré models?
Precisely. It's the key transformation between the Poincaré half-plane model and the Poincaré disk model. Same geometry, just different views, and Cayley provides the lens.
A universal key, almost. And I also heard engineers use this, impedance matching.
Yes, absolutely. Electrical engineers rely on it for the Smith chart. It's a graphical tool for impedance matching problems, and the underlying map is the Cayley transform. Huge practical impact there.
Wow. Okay, so real, complex. Does it go further? You mentioned quaternions.
It does. There's a quaternion homography, too, working in 4 dimensions. Useful because quaternions are often efficient for handling 3D rotations, like in computer graphics or robotics.
Incredible range. But you said it started with matrices. Let's circle back to that. The foundation.
Right, the matrix map. This is often seen as its origin point. It transforms a skew-symmetric n-by-n matrix A.
Skew-symmetric, where the transpose is the negative of the original matrix, right?
Exactly. It takes that A and maps it to a special orthogonal matrix Q using the formula Q equals I minus A times the inverse of I plus A. And Q represents a rotation.
So it links this algebraic property, skew-symmetry, directly to a geometric action rotation. There's that 2 by 2 example, isn't there? With tan theta 2.
That's a classic one. You have a skew-symmetric matrix with entries 0, tan, minus tangent 0. And the Cayley transform maps it straight to the standard 2D rotation matrix, cos t sin centiki cos t.
Very neat. But it has that one limitation, right? It can't produce the 180-degree rotation.
Yeah.
The minus identity matrix.
That's correct. The matrix Q, I is excluded because it would require I plus A to be non-invertible, basically involving division by 0 in the setup. It's a condition. Q can't have art1 as an eigenvalue. Usually a minor point in practice, but theoretically important.
And this matrix version works for complex matrices too.
Yes. The concepts generalize nicely. For complex matrices, orthogonal becomes unitary, and skew-symmetric becomes skew-Hermitian. The structure holds.
Okay, the consistency is remarkable.
Yeah.
And you mentioned even more abstract spaces earlier, Hilbert spaces.
Indeed. The most general and perhaps profound version is the operator map. This applies the transform to linear operators acting on infinite-dimensional Hilbert spaces. So now we're mapping essentially infinite matrices or operations on functions.
Mapping operators. Functions. Wow. That's deep into functional analysis territory.
It really is. It's a cornerstone tool there, linking self-adjoint operators, the infinite-dimensional analog of symmetric Hermitian matrices, to unitary operators, the analog of orthogonal unitary matrices.
So, summing this up, we've journeyed from real numbers, complex planes, quaternions, matrices, all the way to these infinite-dimensional operator spaces, all connected by this this single Cayley transform idea, it really does seem to be this multifaceted bridging tool.
It truly is. It elegantly connects seemingly disparate concepts, simplifies problems across different fields. It really makes you wonder, doesn't it? How can one core mathematical idea act like such a universal translator? It kind of pushes you to look for those underlying simple unifying principles elsewhere, not just in math, but maybe in any complex system. That search for elegance can be very revealing.